Alright, this week we're going to look at another one of these early integrated circuits by Tesla, and this one is called the MA3000. It comes in a very similar package to the chip we looked at last week, although this one is a little bit less tall, and we don't have the military version. And I think this is also why the legs aren't gold-plated. But I can't verify that. So, what does this chip look internally like? This is the internal diagram. At this point, I have to say there is two more chips that look very much like this, and I think it's safe to assume that the MA3000 is a clone of the CA3000 by RCA that I think was on the market a little sooner. There's also a Russian chip that is very similar to this. I ordered some, but unfortunately they haven't come in yet. And with the Easter holiday and everything, I don't expect them to come in, and I want to release this video now. So instead we can have a look at another chip that comes in the same package. It's another chip. So you just imagine the chip I want to show you here looks like this. It is super cool. Ceramic surface mount. Russian packages. These look a lot like the chips they used on the Apollo guidance computer. This is just early IC packaging technology. So this is the internal diagram of this chip, which comes out of a very, very helpful book that has a lot of data on these Tesla ICs. Unfortunately, it's in German, but you can still use the diagram. So, if we look at this, it's fairly easy to see. This is a differential amplifier, and it's very similar to a long-tailed pair. So, if you look at the long-tailed pair here side by side, you can see supply is coming in through this pin 9 here. It's going down to this transistor through this resistor here. And the output is derived from this point here, just below the resistor. But what we have is we have two transistors in the Darlington arrangement, which boost the gain of this. So we have a higher gain and higher amplification. That makes it a better differential amplifier, I suppose. Although how you define better is another thing. Then we have two resistors here. And now in the classic long-tail pair, we just have a resistor here that's providing our bias. This is not ideal though. So what they did here is they put in a constant current source with this resistor here. And below here we have a fairly classic constant current source if you compare it to this constant current source here. Transistor, diode, resistor, load. It's all sort of looks like that. So they also give us a couple of points to manipulate this, so we can not only use this as a differential amplifier, but also do other interesting things and shove the bias around and that sort of thing. So because this is basically that's actually a list of TTL chips. Because this is a clone of the CA3000 by RCA, we have an English datasheet here we can have a look at. My camera would focus. So input offset voltage 6 millivolts, input offset current, it's all not that interesting. Device dissipation We've got maximum output voltage of 5 volts, and we've got 28 dB of gain, single-ended. And if you look at this, you can see the CA3000 is very much identical. They don't give us the resistor values, but I'd be surprised if they were very different. There's an additional resistor here in this circuit, but the rest is pretty much identical. So that is that. There's this also from this book. We have a couple interesting graphs here. So this is the differential gain in dB versus the voltage on this point 2 here. You can see that we can vary our gain by biasing this point 2. And if we just connect it to ground, then we get the maximum gain. And we can also cut it off by biasing this off. So this is fairly interesting, and that opens up a lot of applications. In terms of frequency, you actually see this is usable up to relatively high frequencies at 10 to the power of 6 hertz, which is 1 megahertz. We still have a gain of 28 dB into a load of 5 picofarads, it says here. So I think it is time that we actually look at some dye photographs of this. While experimenting with this, I broke one of the chips. I broke off one leg, unfortunately. And so I had the opportunity to open it up and take a couple of photographs of the dye. So here's the first picture. And we can see this is a fairly early integrated circuit. The die is about 3 millimeters in diameter both ways. And you can see the structures are, compared to modern integrated circuits, they're very, very large. You can almost make out the structures just looking at it with your bare eye, which you certainly can't on modern integrated circuits. I then tried to etch off the metallization layers so we could have a look at the silicon below. Unfortunately, this was fairly hard to dissolve. I used the same process that I usually use when I do this to modern integrated circuits, but it took a long time to dissolve. I don't know if this is due to the just generally larger structures, and so you have more metal thickness. I don't know, or if they're using some sort of weird process. It would actually be very interesting to know what process they use to produce this. Because the dye looks, compared to modern ICs, it looks weird. We can also see on the bottom there's a mark. It's not a Tesla mark or logo that I recognize, but yeah, that's there. Don't know who actually manufactured this. I think it was Tesla. Everything that I read tells of this being made by Tesla. Okay, so that's unfortunately as far as we can go, because I wanted to put the chip into the etching solution again, but unfortunately while doing so I dropped it and can't find it anymore. It's lost in the carpet somewhere forever. So the next thing that we should look at is a little demo circuit. So here I channeled my inner Jim Williams and built a little dead bug style test circuit. So you can see the chip is stuck down here in the middle. We've got the feedback network from the output to one of the inputs, which is also connected to ground through this resistor. And this is just giving us a basic differential amplifier with a single-ended input. Very similar to what you do to do this just with a long-tailed pair. Or also fairly similar to what you do with an op-amp. I've got the input here, the other input here, that has a little resistor on it. We've got the two outputs here. One is going into the feedback circuit, and the other one is here. We've got our differential input voltage, V plus, V minus going in here. We've got pin 2 connected to ground to give us maximum gain, as we saw in the chart before. And 4, 5, 7 are not connected. So I'll hook this up and switch the camera over to the oscilloscope, and then we can have a look at the performance of this circuit. So just a quick look at our test setup. We've got a signal generator coming in here to the input. We've got power coming in here, plus and minus 6 volts. We've got the ground of the power supply hooked up here, and we've got 2 oscilloscope probes on either output. Alright, here we have our test setup. The bottom trace, just for now, is the input signal. This is about 100 millivolts. It's 100 millivolts per division, and this is just about one division. I don't know if you can see it on the video. This upper signal here is one of the outputs, and this is on 1 volt per division, so it's about 5 volts output. I'm going to change this back to 1 volt per division, and I'm going to change over the probe to the output here. And now we can see here's our 100 Hertz signal, and we're getting almost perfect inversion. So we have a differential signal. They're both about the same amplitude. They look very, very clean. If you have a look at this, it all looks very nice. So same obviously goes for sine. If I change this over to a sine, it looks just about as good as the sine wave coming out of my signal generator, which isn't all that great, but that's that. So I'll change it over here, and we can see how far we go. If I change it to 1 kilohertz, or sorry, 10 kilohertz. See, this is just about the same. We have about the same gain, and we're not surprised by this because if we remember the graph we looked at earlier, it was at around a megahertz where we really got significant reduction in gain. So let's try that. Let's go up to 1 megahertz. And you can see that my signal generator isn't actually all that great at 1 megahertz. So we're just going to do sine, because at 1 megahertz on my signal generator, everything you set looks like a sine. But we can see we've got a significant reduction in gain. Now we've got only about 1.5 volts peak to peak, where before we had 5. But I mean, this is 1 megahertz. This is fairly impressive for a chip made in the 70s, and it's still, the signal looks very, very clean. I can do here, I can crank it up to 2 megahertz, and we can see we're really losing gain now. Although the signal still looks very good. We have no visible distortion, I think. We just have a significant reduction in gain. So I think that's all that I have to say about this chip for now. I thank you for watching this, and I'd hope to see you in 2 weeks when I will release the next video.